Hello, I'm Katherine Paul, and today I'll be reading The Mystery of the Largest Light in the Sea by Alex Riley from Nautilus magazine. A quarter mile below the ocean's surface, in the borderless realm of the midwater, two blue-green orbs illuminate the inky black. They glow for a few seconds, then disappear. When they return, it's for the same duration, the same disappearance. It's a signal, a message, the Morse code of an ancient language of light. Friend or foe, rival or mate, I am here, I am this. These orbs belong to Taningia danae, a species of deep-sea squid who can grow to more than 7 feet in length and weigh more than 130 pounds. Also known as the danae octopus squid for their 8 arms and lack of feeding tentacles, these animals glide through the depths on a pair of huge muscular fins that unfurl from their maroon-colored body or mantle. Their arms are lined with 2 rows of sharp retractable hooks, and, like most deep-sea squid, they are adorned with light organs called photophores. They have some on the underside of their mantle. There are more facing upward near one of their eyes, but it's the photophores at the tip of 2 stubby arms that are truly unique. The size and shape of lemons, each nestled with a retractable lid like an eyeball in a socket, they are by far the largest photophores known to science. A lot of deep-sea animals have a tremendous number of photophores, says Sonke Johnson, a visual ecologist from Duke University. But the individual photophores themselves are not that big, typically on the order of a couple of millimeters. I think that's why Taningias are so fascinating, just the sheer size of them. And yet, despite their size, and despite the near global range of Taningia, we know very little about the function of these photophores. We have only seen them glow a handful of times, often in very unnatural settings. To truly understand these light organs, it turns out, we might have to switch our lights off. Bioluminescence is a novelty to us terrestrial mammals. The green glow of fireflies on a summer evening or the glowing algae along the shore are as close as we get to being surrounded by living light. But dive down into the ocean's depths, past the beginning of the midnight zone, where no sunlight penetrates, and it is the norm. Drag a net behind a ship almost anywhere in the ocean below the edge of darkness, and most of the animals you bring up in that net will make light, writes oceanographer Edith Witter in her book, Below the Edge of Darkness. We're talking about a world teeming with light makers. Single-celled algae use it to scream in alarm. Crustaceans produce a stream of electric blue vomit to distract their predators. Countless fish use it to lure prey to their fang-toothed maws. It is even said that giant squid can spot the outline of sperm whales on the hunt as they ripple through bioluminescent algae. In darkness, evolution proceeds in a symphony of blue light. This dominance of bioluminescence, however, does not mean that the deep sea is a constant riot of light. Producing light is expensive, a reaction of molecules, luciferin and luciferase, that are a luxury in a place where food is scarce. It is also risky. To turn a light on is to risk drawing unwanted attention, and there are always hungry eyes scouring the darkness for a glimmer of opportunity. The deep sea isn't an amazing collection of light, Johnson says. It's an amazing collection of potential light. So why do Taningia invest so much energy, place themselves at so much risk by illuminating the largest photophores in the animal kingdom? Scientific understanding of the squid was long based on what they looked like shortly after they died. Between the 1940s and 1970s, sperm whales were hunted all over the world for their oil, their blubber, and their meat. Cephalopod researchers would be sent their stomach contents, and since these whales were often slaughtered soon after they had surfaced from feeding, The squid could be well preserved, a rarity for such a fragile animal. Some of our best information about how big these animals get comes from that old data, says Jesse Kelly, a researcher from Dalhousie University, Nova Scotia, who recently finished his PhD on the taxonomy of octopus squids. Even in death, the beauty of the light organs is plain to see. They're white with that kind of iridescent sheen that the light can play with, shifting between hues of pink and green, says Kelly. In life, this massive pearlescent tissue glows with the cold light of blue bioluminescence, a glow first seen by humans in 1975, the year researchers dropped a fine meshed net from a boat off the coast of Oahu, Hawaii. Working at night, they were investigating one of the most common uses of bioluminescence, camouflage. By producing a soft glow on their undersides, animals can hide their dark silhouette from predators looking up from below. This is known as countershading. As the researchers pulled in their nets, they noticed a tiny Taningia, the length of an index finger. While the squid also had countershading photophores, they were desperate to investigate the unusual arm tip organs. First described in 1931, no one had actually seen them glow. They placed the squid in a shipboard aquarium and turned the lights off. After their eyes adjusted to the dark, one of the scientists gently stirred the water with his hand. Flash! A second of blue-green light, as they described it, was followed by the squid wrapping their tentacles around a finger and delivering a tiny beaked bite. This was the most common response, a bite. But in some cases, the Taningia would flash their photophores and swim away from the hand, a retreat. Both behaviors seem to have the same function, stunning the visual system of another animal, prey, or predator. This raised the question of what a full-grown, 7-foot squid might hope to stun. Hunted by 230-foot-long sperm whales, elephant seals, and deep-sea sharks, perhaps these photophores are so large because they need to stun some of the animal kingdom's largest eyes. Although whales rely on echolocation to locate their prey in the depths, for the last few seconds of the hunt they rely on vision. If, in that final moment of attack, they meet with a bright retina-bleaching flash, a Taningia might use the ensuing black spot to make a narrow escape. Plausible as this is, though, there is no direct evidence of such behavior in the wild. In fact, a camera attached to an elephant seal's head captured a Taningia hunt. The glowing arm tip photophores dip in and out of the frame, but there is no flash. After 30 seconds of pursuit, the seal catches the squid. Were the photophores mere decoys to distract the seal away from the squid's head end, the butterfly eye spots of the deep sea? With animal-borne video cameras becoming commonplace, new recordings could easily overturn this brief insight. While there are very few reports on their retreat behaviors, evidence of Taningia on the attack is ample. Much of it comes from a 2004 expedition by Japanese researchers seeking the first images of a giant squid, Architeuthis, whose mantles alone can grow to the length of an entire Taningia. They hope to lure a giant out of the darkness with a bait of dead mackerel and Japanese common squid. They captured one now famous giant squid image, but their cameras were spoiled for Taningia. Out of 26 deployments, they recorded 12 interactions. Friend or foe, rival or mate, I am here, I am this. Until then, Taningia were thought to grow into relatively gentle giants, largely due to the ammonia-filled pores that give their tissues buoyancy at depths, but also make them very squishy and presumably too delicate for a predatory lifestyle. Instead, Taningia showed themselves to be agile, active, even aggressive. They attacked the bait, the lights illuminating the bait, the nylon line, all wrapped in 8 arms lined with sharp retractable hooks. Before each attack, the squid flash their photophores, just like the tiny Taningia from 1975. This emission may work as a blinding flash for the prey, as well as a means of illumination and measuring target distance in an otherwise dark environment, wrote the expedition's researchers who were led by Tsunemi Kubodera from the National Science Museum in Tokyo, Japan. In 2020, a very different range of Taningia emerged during an encounter with the Schmidt Ocean Institute's remote-operated submersible. As it sank, a large squid appeared, bathed in a halo of artificial light. The two lemon-sized photophores glowed like green floodlights. While their intensity was misleading, a result of the submersible's beams bouncing off the reflective layer of tissue behind them, this individual had clearly opened their photophores. The blue-green bioluminescence was masked, but it was there. The whole scene lasted 20 seconds or so. There was no sign of aggression, no bright flash before an attack. If anything, the behavior intimates a sense of intrigue, even an attempt at interaction. This is why Kelly finds Taningia's light organs so fascinating. Not just their size, or their pearlescent quality under dissection, or what they represent. They are very suggestive of communication, he says, which we're obsessed with because we're such a social species. With photophores open, the squid hovered in the blue, as if waiting for a response. When none came, they casually unfurled their muscular wings and with one powerful stroke, drifted backward into darkness. Thank you so much for listening to this story with me today about Taningia and their incredible journey in the world. I'm KP, Katherine Paul from Black Belt Eagle Scout. I'll be on the road all year long. Just visit my website, blackbelteaglescout.com, for tour and show information. Have a good day.